Today we're going to talk about complex numbers and how it relates to what we've been doing so far with polynomial functions. And then we'll also talk about the fundamental theorem of algebra. So complex numbers, these include all real and imaginary numbers. Now, any complex number can be expressed as in the form a plus bi, where a represents the real part and b represents the imaginary part. So since any complex number can be written this way, if it's just a real number, then the b value would be equal to 0. So the imaginary unit, remember from Algebra 2, is represented with the letter I, and it's equal to the square root of -1. And then another thing that we are going to talk about is what I'm going to call the cycle that I goes through. It's being called I cycle. So I to the first is equal to 1. I squared, so if you take the square root of -1 times the square root of -1, that's equal to -1. Now what about I to the third? I to the third is going to be the same as I squared times I, so you're going to do -1 times I, which is -I. I to the fourth, you can think of this as I squared times I squared, which is -1 times -1, which is +1. Now we get to I to the fifth, and that's the same as I to the fourth times I, so 1 times I is equal to I. And you might be thinking now, oh, now it's going to start repeating itself because I to the sixth is the same as I to the fifth times I, which is I times I squared, which is equal to -1. And so there's this cycle of length 4 that continues as I is raised to another power. Now we can use the fact that this is in this cycle to help us simplify I when it's raised to a very high power. So for example, if you were asked to simplify I to the 243rd power, what you can do is you can take the 243 and you can divide it by 4. Why 4? Because the cycle, that I being raised to a power, has a length of 4. So if we divide this by 4, so divided by 4 we get 6, multiply that we get 24, subtract, we get 0, bring down the 3, and that doesn't go in, so our remainder is 3. Now the reason I'm doing this out by hand and not just using a calculator is because we want to know what the remainder is. The calculator usually, depending on the setting that you have it on, but usually it will give it to you as a decimal, right? It will automatically already put it over 4 for you, which is fine. You just need to know that 0.75 means that it's a remainder of 3 because it's 3 over 4. So since it's a remainder of 3, what this means is that this I to the 243rd power is the same as I to the third power. And I to the third power is something that we can come up with much more easily, because I squared is equal to -1, so -1 times I is equal to -I. Okay, we're going to take a look at some examples of complex numbers and doing operations on them. So example 2, if you add complex numbers, you want to add the real parts together and add the complex parts together. So here, we're going to add the 3 and the 2, so that's 5, and then we're going to add the -I and the positive 3i, and that's positive 2i. So this is equal to 5 plus 2i. Okay, now subtracting complex numbers. So same thing, we are going to combine the real parts, combine the imaginary parts. Now for subtracting, you just want to make sure that if you are subtracting a parentheses, that you do, in fact, distribute that minus sign. So I'm going to do that first. So 3 plus 0i plus 2 minus 3i, and that's equal to, when you add the real parts, 3 plus 2, And then the imaginary part is 0i minus 3i. That becomes 5 minus 3i. And that's your answer. Okay, now what about multiplying complex numbers? So when we multiply, we are going to treat it very much the same way. The only thing is that our answer at the end, we want it to have a real and an imaginary part, and that's it. So if you end up with I to any power, you are going to want to simplify that down. Okay, so let's go ahead and multiply. So 2 times 4, that's 8. 2 times 3i, that's 6i. Negative I times 4 is negative 4i. And negative I times 3i is minus 3i squared. Let's combine some like terms there. So the 6i minus 4i is 2i. And now this 3i squared, since I see I to a power, we want to simplify that down. So I squared is equal to negative 1. So I'll replace the I squared with negative 1. And that becomes a positive 3. And now I can actually add those together. So the 8 plus the 3 gives me 11 plus 2i. And that's our answer, with a real part and an imaginary part. Now let's talk about dividing complex numbers. Now, when you're dividing complex numbers, really what you're going to do is you're going to try to avoid complex parts in the denominator by multiplying by the complex conjugate. Now, what's the complex conjugate? Well, so for example here, since we see the imaginary part in the denominator, the 4 minus 2i, now remember we want to get rid of complex parts from the denominator. Multiplying by the complex conjugate means you take that 4 minus 2i, and because it's a complex number, we call it complex conjugate, but the conjugate is really just changing the sign between the two terms. So what we're going to do is we are going to multiply by 4 plus 2i. Now if we do that to the denominator, we also have to do that to the numerator. That way we're multiplying by a form of 1. So let's go ahead and multiply that all out. So 2 times 4 is 8, 2 times 2i is 4i, 3i times 4 is 12i, 3i times 2i is 6i squared, and then on the bottom we have 4 times 4, that's 16, 4 times 2i, that's 8i, negative 2i times 4, that's minus 8i, and then 2i times negative 2i is negative 4i squared. We can combine some like terms there. So the 4i plus 12i will combine, the 8i minus 8i will combine, and then anywhere I see an I squared, I'm going to change that to negative 1. And then we are going to simplify this down. So the 8 minus 6 is going to be 2, so 2 plus 16i. And then on the bottom we have 16 plus 4, which is 20. And then we're going to separate this into the real and imaginary part. So this will be 2 over 20 plus 16i over 20. And then we can simplify each of those fractions. So we have 1 over 10 plus 4i over 5. And that's our answer there. Okay, so that's complex numbers. Now we're going to talk about the fundamental theorem of algebra. So the fundamental theorem of algebra says a polynomial of degree n, where n is greater than 0, has exactly n complex roots. Now if a polynomial has an imaginary root, then its complex conjugate must also be a root. So that's the fundamental theorem. So first, that a polynomial of degree n has n complex roots. Now remember, complex means it covers both real and imaginary roots. And if a polynomial has an imaginary root, then you know its complex conjugate must also be a root. Let's do an example. Find all roots of f of x equals x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60, given that 1 plus 3i is a root. So first off, if you look at the polynomial, you'll see that this is a polynomial of degree 4. That means that this must have 4 roots. Now you're told that 1 plus 3i is a root, so that is a complex, in particular, an imaginary root. Since it is an imaginary root, you know that its complex conjugate must also be a root. So not only is 1 plus 3i a root, you know that 1 minus 3i is also a root. So I'm going to write out the factors here. This would be x minus 1 plus 3i. And then we also know the complex conjugate is also a root. So I'm going to write down x minus parentheses 1 minus 3i is also a root. Now because it's degree 4, we know that there must be 2 more roots that we haven't found yet. So I'm going to just write them off to the side here as x minus and x minus. Right, and just leave a blank space there, just for a visual. Now what I'm going to do first is I'm going to simplify these first 2 factors, and I'm going to actually multiply them together. So I have x minus 1 minus 3i and x minus 1 plus 3i. Now if I multiply this all out, we're going to have x squared minus x plus 3ix minus x plus 1 minus 3i minus 3ix plus 3i minus 9i squared. Now you might be thinking, this makes it a lot more complicated. It does at first, but let's see what we can cancel out. So we have a positive 3ix and a negative 3ix. We can cancel those. We have a minus 3i and a plus 3i, so we can cancel those. And then the minus 9i squared, I squared, remember, is equal to negative 1. So if you multiply negative 9 by negative 1, that's plus 9. So we can actually combine what we have left. So we have x squared minus 2x plus 10. So this whole thing multiplied out is x squared minus 2x plus 10. Now, we are trying to find what the remaining roots are. So what we're going to do is we are going to divide out the roots that we already know. Well, since we combined it into x squared minus 2x plus 10, let's go ahead and divide that out. That's going to mean that we're going to have to do long division. Okay, so set up your long division. Let's divide out x squared minus 2x plus 10, divide out the roots we already know, and see what we have left. Remember that after we've done this division, we should expect that the remainder is equal to 0 because these 2 numbers are factors. Okay, so let's do the division. So on top here, this will be x squared, multiply that, x to the 4th, minus 2x cubed plus 10x squared, subtract. That leaves us with negative x cubed minus 4x squared, bring down the 2x, divide again, we have minus x, multiply, we have negative x cubed, positive 2x squared, minus 10x, subtract, change all those signs, we have negative 6x squared, plus 12x, bring down the minus 60, and do it one more time. So negative 6 goes up on top, multiply, we have negative 6x squared, plus 12x, minus 60, and subtract, change all those signs, and all of those should cancel out. That gives us 0 as a remainder, which is what we expect. So those last 2 factors that we weren't able to completely write out, where we just wrote out x minus and x minus, this should multiply to x squared minus x minus 6. Now, let's see if that's factorable. So if we try to factor that, that is in fact factorable. It becomes x minus 3 and x plus 2, which means that our roots are at 3 and negative 2. So find all 4 roots of this polynomial. Well, that's 1 plus 3i, 1 minus 3i, 3, and negative 2.